a look. This is, again, test 7. Okay, this is test 7. What sections? What sections are we on?
12:1 to 4.
12:1 through 12:4, and what else?
13.
Yeah, and 14-1, okay? 12:1 through 12:4 was all about simple harmonic motion, vibrations, oscillations, mass spring systems, pendula systems. And then 14:1 was on characteristics of light. Okay, the basic, the introductory stuff for light. And those problems on the test, I'm hoping, are kind of like gimmies, okay? Because we haven't really gotten to a lot of the depth when it comes to light. When we do the other stuff in chapter 14 and 15, we'll see that it becomes a little more complicated and we learn a little bit more about the physics behind it. Whereas this was more just an introduction, okay? I hope everybody did what I asked them to do when it comes to keeping up with your homework and problem sets so that tomorrow your problem sets are here on time. I'm going to tell you now, I'm not going to put the solution up to the problem set. The reason being, the folks on Kairos are not going to be turning it in until next week on Tuesday. Okay, so I'll tell you right now, I will not be putting that solution up, unfortunately. But if you would like to, if you'd like to come either check your answers with me to see the even numbers, and you want to come do that tomorrow, you can do that to see that you got the right answer for the work. I have all the solutions already, so you can come by and just ask me and we can go over it. So if there was a problem that you're confused on, please go ahead. If you turn in hard copies normally for the problem set, and you want to just photocopy yours before you turn it in tomorrow, it might be a good idea if you want to use it to study from, because again, the solution's not going to be posted. Okay, so just to give you a little heads up ahead of time.
Are we allowed to go over it with, like, are we allowed to ask questions about problems before we hand them in?
Sure, people come in all the time and ask me questions about it. That's fine, yeah. So if you had like a question, come by today and you want to ask me, sure, absolutely. Today's a B day. I think it's because of Coffee House, right? What time does Coffee House start at?
No, Coffee House is that late.
Yeah, I think the B-Day just had a B-Day.
Oh. I think it's because of Coffee House. That's what it said on the schedule. Anyway, what I was getting at was, if you have free time after school and you want to check some stuff, just come by right after school. If you think you're going to be a little bit later, let me know, so I know to wait. All right. Let's begin taking a look at each of these sections. So, 12:1, let's start with. 12. What was the beginning in 12:1? What do we look at?
Negative F, E.
Fs equals, Julian? Negative kx. Now, somebody remind me, this is good for conceptual kind of questions. Why is there a negative physically, not mathematically, but physically? Why is there a negative in this formula, Julian?
Because we're talking about the force that the spring is applying, and so in order for a spring to apply force, you need to be applying some sort of thing to the spring. So like you're either pulling the spring or compressing it, and when you pull the spring, it's trying to get itself to go back to its equilibrium state. So it's pulling against the force. So your force would be positive, so you may be pulling it to the left, but the spring itself will want to pull back to the right.
Very good, very good. So if you're pulling left, if your displacement or your force applied is left, the spring pulls back to the right. So the force and the displacement are in opposite directions, thus this negative sign is occurring here. Okay, that's where that comes from. So again, if the force of the spring is going to be an answer that's going to be positive here, then we're going to have a negative, making this side also positive. Okay? So that negative sign is very important. So when you work on this and you go through your work, and if you get a negative answer for K, you got to stop and think to yourself, what did I do wrong here? K cannot be a negative value, right? K is your spring constant. It's not going to be a negative answer. So that's the importance there for that. What are the units? What are the units on K? If, let's assume our displacement is in meters and our force is in newtons. Newtons per meter. Okay, and that makes sense. We have newtons equals, and I'm just looking at units, newtons per meter and meter. If your displacement is given in centimeters, then your K value is just in newtons per centimeter. Okay? Or you can convert to meters if the K is given in newtons per meter. But it depends on the problem. Again, if a problem is given to you where the displacement is in centimeters and you have the force and you want to solve for K, you could convert this to meters, or you could go through it with centimeters if you want to, but then just write newtons per centimeter as your units for K. But you need to be consistent. Either convert and use newtons per meter, or don't convert the centimeters and make K newtons per centimeter.
Would you take off if you left it in newtons per centimeter?
No, that's fine, but you need to know that if you're given a K value in newtons per meter, and you're given a displacement in centimeters, one of those needs to be converted, right, to get newtons back out. So keep that in mind, okay? But yeah, if you're given the force and you're given the displacement, you can leave the units the way they are and just give your K value and whatever was given, okay? Let's see. What about, we talked about a spring that's in equilibrium state and then pulled completely and then it's released. It's going to oscillate back and forth, right? And that's that simple harmonic motion. What are some characteristics about that oscillation? What are some interesting things that we pointed out? And we did that with a diagram where the mass was moving back and forth. We talked about velocity, acceleration, we talked about the force. Tristan.
The velocities were zero on the ends, but the accelerations were their highest, and then in the middle, the velocity is the highest, but the acceleration is zero.
Yeah, that's absolutely exactly right. Good, Tristan. Okay, at the ends, when the spring mass system gets stretched, it stops, right? And then it comes back and it compresses and then it stops. And then it comes back and it expands and it stops. So every time it gets to the end or to its maximum amplitude or displacement, the velocity is zero. It pauses at the endpoints. But then when it starts to get pulled back, the spring gets pulled back, it picks up speed until it gets to the middle. And there at the middle, its velocity is at a maximum, or its speed, we should really say, is at a maximum. The velocity could be negative or it could be positive depending on which way it's moving. At the endpoints, when I've completely stretched the spring, the force is at a max, right? The force is pulling back, and it pulls the spring mass system until it gets to equilibrium. Then there's no force for a little moment of time, but its inertia continues to carry it to then compress the spring until there's a lot of force in the spring, and the force is at a max again. Then the force pushes back until it's back to equilibrium, and there's no force again at equilibrium. So at that equilibrium in the middle, as Tristan said, there's no force, and the speed is at a max. When the spring is stretched at its furthest amplitudes, there's no velocity, but the force and acceleration are there at a max. Okay, and that's that diagram that we looked at that showed the 5 different stages.
At equilibrium, is acceleration zero?
Yes, whenever force is zero, acceleration is zero. Remember Newton's law, F equals ma. If the net force is zero, it has to be zero acceleration. So that midpoint, or that equilibrium stage, is where there's no force, equilibrium, right? No force, equilibrium, and thus no acceleration there as well. How about for a pendulum? How is this analogous? Who can describe a pendulum's motion and how it's analogous to the situation that we just went over? How is it really the same thing as the spring mass system? How is a pendulum the same thing?
Well, when a pendulum's swinging, when it gets like as high as it gets there, the y max, the velocity is zero.
Yeah, it stops, okay?
And then the acceleration is zero. Or no, just acceleration is always there.
Acceleration is always going to be there,
No,
believe it or not, for a pendulum.
when it gets here, something happens.
Something does happen.
Acceleration stops. So is there force?
It doesn't really stop there. Be careful, because now we're looking at gravitational acceleration, so it's always there. But what's the key with the velocity there, actually? That's the important part.
Oh, zero.
Zero at the top.
Zero at the top, and then half at the bottom. I don't know.
Think about kinetic energy, potential energy, right? Isn't it all kinetic down here? So what is high at the bottom? The amount of velocity is very high. Then it slows down, it slows down, it slows down, it stops. Velocity is zero. Picks up velocity, picks up velocity, picks up velocity, V max, slows down until V is zero. Okay, those are the important parts for the pendulum. The acceleration portion is a little bit difficult to describe simply because there's always gravitational acceleration, really. Okay? The other part about a pendulum, what causes the pendulum to seek out that equilibrium state? What force? What is the restoring force for a pendulum that causes it to want to move to the equilibrium position? It passes it and it comes back. It passes it, but it comes back. Why does it keep coming back? What's pulling it back? Yeah, gravity. Okay? So the spring force in a spring mass system is like the gravitational force in a pendulum system. Julian.
So, is the acceleration, so the acceleration would not be zero at the equilibrium position in the pendulum as it passes by.
No, it
That's
would
how
not.
the textbook, when it gives you the spring.
I know.
That's how.
That's a little bit of a discrepancy because of the gravitational acceleration there. Because it's going to be, technically speaking, at the bottom there, it's no longer moving up and down. Its vertical velocity component has become 0. So you could say that the vertical, well, there still is acceleration because of gravity though. So we're going to try and stick with the analogous portion being the velocity is changing along the
Because
way.
there's a question on the problem sets that asks like, what's the relationship of acceleration in a pendulum, like when and how it changes. Like it asks.
Read the word. You have the exact
I
word?
don't have the exact wording, but it asks you about acceleration in springs and pendulums. It asks you to look at the graph the image rather, where it shows you where the acceleration is.
Is that in a book with them? What page you want to read?
469, number 3.
Number 3? Does the acceleration of a simple harmonic oscillator remain constant during its motion? Is the acceleration of a zero explained? Well, this is talking about, well, they don't talk about whether it's a spring or a pendulum.
Rotating a point from an angle theta, rotate points.
I'm assuming they're discussing or they're referencing a spring and not a pendulum, because it's from the first section. It's from section 12.1, that question?
So, do you like biology?
But in 12.1 it's probably both.
Matrices to calculate the evolution of
Talking
biological
about both 12.1 or
population.
12.2 we started with.
Or deer. I'll explain.
Because I do remember the.
Yeah, now it is in the diagrams we talked about, right? Let me think about that, Joanne. Because technically speaking, there is still acceleration there.
Should we the answer? Can we close, can we?
Trying to think about components of acceleration. Let me think about it, Joanne. I'll be back for sure. Alright. Because that is a bit of a discrepancy. What else did we do in 12.1 and 12.2? 12.1 and 12.2. Come on, we did something else, people. What else did we do in 12.1 and 12.2? We looked at waves. Yeah, we started thinking about the fact that they're waves. What else? Tau. What does tau represent? Yeah, the period of oscillations. And we discussed the fact that the two situations are analogous. Okay, and remember our formulas, and you're going to be given these, but remember that tau equals 2 pi radical L over G for a pendulum.
I know it's 12 too.
Say again?
I know it's 12 too.
Yeah, I said in 12.1 and 12.2, what else do we do? And 2 pi square root of m over k. All right, and again, these are analogous to one another. So what can we see from this? What can we see? The period of a pendulum is affected by the length and the gravitational pull on the planet. What is it not affected by that's not obvious, but you noticed in your lab, Julian? Mass.
Has no effect.
Okay, mass has no effect on the period of a pendulum. On the period of a pendulum. But for a mass spring system, the factors that affect the period are the actual mass of the block or object, and K or the spring constant. Now, make physical sense of these relationships. Here, as K goes up, what does that mean about the spring?
It's for every unit of distance pulled from equilibrium position, there's more energy added to its force pulling back towards it.
Yeah, so more force is needed, right? More force is needed.
More force needs to pull it off, and now it's also pulling back harder.
Thus,
Thus, I mean,
what would happen to the period if the
it would go down
increase? Yeah,
because
it's a more rigid spring.
there's more force to pull it back. That change will happen more quickly.
Yeah, think about a spring. Remember there was the spring in your lab that was really weak? And when you put the mass on it, it stretched a lot. It was the wider diameter. By the way, that was just a coincidence. Some of you answered that. I didn't take no points for it. But the wider diameter and the smaller diameter is not what's affecting really the K value there. I mean, it has a component to it, but it also has to do with the number of coils, the actual material, the thickness of the coils. There's a lot that goes into the actual K value. It just happened to be that the lower K value was the bigger diameter, and the higher K value was the smaller diameter.
Wait, which question was
Okay?
that?
It was in the lab. There was a question in there.
Like which one you expected?
Yeah, I think it was like the expectation. Some people expected one to be one, and then it was the reverse. It just happened to be that way in the lab. I was just
But
curious.
that's what the question was about, right?
Yeah, that's all I was referring to. But it's not like, some people generalized and wrote at the end of the lab, we could say in general that bigger springs or bigger diameters have smaller K values. That's not always true. It just happened to be that way. Anyway, back to the question. The bigger spring was able to stretch much easier, right? The bigger diameter. Because the K value is much smaller. So if you put the mass on there, it would oscillate a lot more from the equilibrium, and it would take longer to complete an actual cycle. But the spring that was really rigid, the spring that was strong, only oscillates a little bit, and thus its period is lower or a smaller value. So as K goes up, as the spring gets stronger, the period of oscillations goes down. And that's this inverse relationship again. Okay, inverse relationship. What about the mass here? As the mass goes up of the object that's attached, what happens to the period?
Gets lower. How goes up?
Goes up. It's in the numerator. Look at the relationship.
Wait. As mass goes up, the tau goes down.
No, as mass goes up, tau goes up.
Oh, that's right, no, sorry, it takes longer for it to get pulled back.
Yeah.
Yeah.
It takes longer. It goes up. You said it goes down the first time. That's fine.
Yeah, that's right.
So as mass goes up, as the object attached to the spring, its mass gets increased, it's going to take longer. And think about, are we all focusing? I'm seeing too many people smiling, looking on their iPad, and that makes me suspicious. I don't want to have to walk around. I mean, obviously, I walk around, but I don't have to stand behind it. If you put a larger mass on that oscillating spring, it's going to cause more amplitude, right? It's going to oscillate further. It's going to pull further down, which makes sense that it's going to take a longer period, longer length of time. Okay, let's go to the pendulum now. The short pendulum string, if you notice, you let go, it's very quick, right? But a longer string, you let go, it's got to follow a much longer path. It's a larger arc length, in essence. That's what you're comparing. You're comparing a little short arc length to a much longer arc length. So it's got to be a larger period as the length goes up. But as the gravitational force goes up, like on Jupiter, you're being pulled to the ground quicker. If you're being pulled to the ground quicker on Jupiter, you'd be pulled down faster. It would be pulling the pendulum faster. So as gravity goes up, the period goes down. Again, denominator means they're inversely related. Numerator means they're directly related. What if I... Can we open the window? Sorry, I'm competing. You talk. Me and Mr. Donchik are both loud talkers, I know that.
Donchik now.
Sure. Absolutely. Mr. Donchik and I.
Oh,
Now,
my windows.
what would happen if the length of the cord connected to the pendulum went up by a factor of, say, 9? 9.
Wait, sorry, can I put my head
If the length went up by a factor of 9, what would happen?
Increase by 3.
Good, because it's underneath a...
Radical.
Yeah, think about it. Put a 9 right here, everybody. Put a 9 in your mind right there. What's the square root of 9?
3.
So it would really be like pulling the 3 out front, right? So if you increase the length by a factor of 9, so I've got a length of a pendulum this long, and then suddenly it's 9 times longer, it will take 3 times as long for it to complete a cycle, or the full period. Now, what if the length went up by a factor of 5? What would happen? The length went up by a factor of 5.
It would increase by a factor of square root of 5.
Yeah, square root 5. Because there's no, remember how earlier we could take the square root of 9 and bring it out as a 3? But if this increases by a length of 5, or a factor of 5, then you're increasing by a square root of 5, which is not an integer value, so you would just say it increases by a factor of radical 5. And what happens to the denominator portions? Instead of increase? Yeah, they decrease. So let's go over here to the mass spring system. If I double the strength of the spring. It means I double the K value, right? It means it's a more rigid spring. The spring is stronger. So it's going to take less time for oscillations to occur. So if I double the K value, I'm decreasing the period by a factor of square root 2, or radical 2. Okay? You're decreasing by a factor of radical 2. All right, James. Hey, what was 12.3? What was 12.3, our next section here? What was 12? Come on, folks. If you don't know at least show me that you're looking at me.
Properties of wave.
Yeah, properties of waves. And what did we talk about? What were the main topics within that? There were several things. It was mainly conceptual, right?
Yeah, it was about the wave, longitudinal.
Versus?
Perpendicular.
Yeah, versus transverse, right? Transverse and longitudinal. A transverse waves. Example of transverse was the EM waves in chapter 14, right? When the oscillations are up and down of the electric field and the magnetic field, but the wave is moving this way. Transverse means perpendicular. Okay? So oscillations are up and down, but motion of the wave is left to right. What was longitudinal? What did that mean?
It was like you slightly dropped in parallel.
Yeah, the vibrations are parallel to the motion of the actual wave. So that was like sound waves. When I talk, the sound molecules vibrate, but they're still moving in the same direction towards your ear. They're vibrating this way, and the motion is this way. They're parallel. It was like the spring where one person held the other end and you just sent a little pulse, and you saw the spring compress the whole way down, and then it compressed its way back. Versus when we had a spring and we went like this, or the slinky, whatever it was. Went like this, and you saw the vibration up and down, even though the wave propagated left to right. Okay, so longitudinal, it's parallel vibrations to the motion. Transverse is perpendicular vibrations to the motion. The other part of section 12.3 that we talked about. 12.3, what else was there besides that? I know we talked about like fixed ends and free ends. Was that 12.3 or 12.4 though?
Oh, 12. Oh, that. 12.4 is free. I think that was
Speed of wave.
Wasn't there a question last
The
time?
speed of waves? Okay.
Like, that's like if it gets reflected or inverted.
Yeah, and inverted. So if I send a pulse down a slinky or some object like a rope and it's fixed to the other end, what's going to happen as a result of that?
Reflected and inverted.
Yeah, it sends the same wave back, but it's inverted now because it causes the rope to pull up on here, and then the rope's going to pull back as a reaction backward. But if there's like a slip knot at the end, and this was the one I was talking about with the mop here, if you had a rope attached to the mop and it was tied lightly, the knot, and you sent the pulse, it's going to cause the knot to kick up. And then the knot's going to slide back down, and it's going to send the exact same reflected pulse back to you. It's not going to be inverted because the knot acts as if it's another person on the other end sending the pulse back to you. Okay? We talked about V equals omega lambda, where the velocity equals the frequency times the wavelength. Velocity equals frequency times wavelength. So the frequency and the wavelength, if you remember, are inversely related. They're inversely related. Let's see. What else did we talk about? Constructive and destructive interference. What is the difference? What is the difference between the two?
Construction interference is when two
Waves?
Two waves impact each other or pass through each other and become like the amplitudes of them add up to the amplitude of a combined wave as they pass through each other. And destructive would be if they were going opposite. If the amplitude was negative in one of them and positive on the other, then the combined wave would have a smaller amplitude.
Okay, very good. So this example, they would pretty much cancel each other out, right? If these two waves met in the middle. If these waves met in the middle, they would cancel because the amplitudes are pretty much equal and opposite. Now, we also talked about, if you're given a graph with waves, how to identify which is the resultant, which is the original. Okay, so let's take a look at an example of that.
So wait, could you like shield from radiation by using more radiation, like to cancel the wave coming at you?
I don't know, it's a good question. I know that they do things like you put like lead, because lead stops radiation because it blocks the waves,
Right.
but does it actually destruct the waves like interference-wise? I don't think so. I don't know, James. It's a good question. I'm not sure to answer that. What if we have just a simple graph? Say we have 3 waves. You okay? Hit your elbow?
Yep.
That's not funny, but I hate that.
It's never funny. We have 3 waves here. We have red, black, and blue on the screen. Now, for these 3 waves, which of them is the original and which of them is the resultant, and why? And why? And why? Julie. Two original.
Okay, so the red and the black one, because the sum of the amplitude of the original one is equal to the altitude, not altitude, amplitude of the
Same word, yeah. Amplitude works too, but amplitude, yeah.
amplitude of the original.
Yeah, again, the sum of the amplitudes equals the resultant. That's the theory of superposition. And we're really literally just introducing the idea of superposition, but when it comes to engineering, it's used in every topic. It's unbelievable how many theories adhere to the rule or the idea of superposition. That the sum of 2 smaller things equals the third, when normally you wouldn't always think that. And obviously you know that a quarter plus a dime equals 35 cents, something like that's simple. But when it comes to waveforms, it's not obvious that they are actually equal to the sum of the 2 smaller parts. Because some things don't follow that rule. Okay, some things don't follow the rule of superposition.
Isn't that like what they try to do with quantum computers instead of having the computations are based on 1s and 0s, it's based on a superposition of it could be either simultaneously, like when they're trying to build quantum computers.
When they're trying to build what computers?
Quantum computers, ones that use quantum effects too.
I've never read about quantum computers, Ian. That's interesting. So it would be working at a higher speed, pretty much?
Yeah. Because in each calculation, each digit could be 1 or 0 at the same time.
That's the idea of binary code and offs and ons and logic.
Right.
I don't know.
On and off at the same time for each calculation. It's calculated parallel, each one, each result.
I'd have to read. I'm interested though. I never heard of that before though. That's really cool. I never heard. Now, if you're given a more complex graph, what would you do to figure out? What would you do to figure out?
You would draw the line down, and then you would add up any two waves to see if it added up to see if it was the sum of the third one.
Yeah, so for example, if you look at the amplitude of the blue wave at that point, and then the black wave, if you added these 2 things together, it would become bigger, wouldn't it? So clearly the red wave is not the resultant. This is an easy example to see here. Okay, even if you added together the red wave and the blue wave, it would get larger than the blue wave, which doesn't make sense. So it's got to be that way. Now, is this constructive or destructive interference? Yeah, it's constructive interference. Because the red and the black wave add together to become a larger wave. Even in the bottom. Even though they're both negative, they become more negative. Right? More negative. We're looking at their absolute values, really. This is a -3 maybe. This one has a -5, making this -8. Okay?
This is
I know it sounds like it's the amount of disruption is the amplitude, more or less. But with EM pulses, what is the amplitude a measure of? The amount of
the intensity. So it depends on what the EM wave is, though.
Right.
Yeah, the luminosity for light. That's called luminosity. Intensity is a general word, but for light it'd be luminosity. For a radio wave, it'd be the strength of the signal. Trying to think about gamma rays and stuff. I don't know. I'm sure the amplitudes are very low on gamma rays that are used for cancer treatment because things are more intense. Yeah, I'm not sure. I think for each one it's going to be a different thing. Yeah. So I wonder what it would be for a visible spectrum.
Wasn't that just brightness then?
Yeah, but I'm wondering how it affects the colors differently. Is it the same for each color, or does it change? I wonder. Is amplitude a function of the actual color as well? Because frequency and wavelength change, which causes a change in color. But I wonder what the amplitude is, if there's a major difference in the visible spectrum of the amplitudes of the different colors or not. I don't know. It's a good question. What was the last thing we talked about in chapter 12? It was one other thing we did in chapter 12. Look in 12.3 and 12.4. Did something else, I remember. Is that it? Could have sworn there was something else that we went over. Oh, there it is. Yeah, go back. Standing waves. Okay, so standing waves. Standing waves, what's our good example to remember for standing waves? That's probably the most obvious example of a standing wave that has a half a cycle. A half a cycle. Luke?
No,
Sure? Standing wave, what's a good example?
Was it like when you did that or something?
No, that's not an obvious example. There was a much more obvious example.
Slinky?
Slinky, sure, but that's more real life that you see a lot.
I guess
Water.
for an example. Standing.
good job, Neil.
It's a really good example of a standing wave that occurs a lot.
Is the standing wave the one where the nodes don't change?
Yes, where there are nodes that are stationary points.
I was gonna say, when you drop a rock in water, but no.
But those waves are propagating
Yeah,
out. They're not
yeah.
standing waves. They're
Harvey?
moving.
Yeah.
Remember guitar string? When you pluck a guitar string,
Oh, no.
if you actually videotape the guitar string vibrating, you would see literally a half wave going up, half wave coming down, half wave going up, coming down. It was that first. It's a half a wave. It's not a full wave. It's a half a cycle in a sense. What the? Oh, there. What? Is anyone else seeing this, or am I crazy right now?
I don't see it, I don't see it.
Just make it graph.
That's wild. What is going on?
Wait, Mr. Up. It says 2 waves for the.
Take a quick break, guys. Take a quick break. Come right back, please.
It says 2 waves.
Yeah, take like a 3-minute break.
The
then come
standing
back.
wave thing, it says 2 waves. So what do you mean? What are you trying to tell me?
What?
It says 2 waves.
That's what it comes as a result of. But I'm saying this would be like one wave or one half of a wave being up and down. This is one full cycle. A guitar string is just a half a cycle vibrating up and down.
Right, well that's because it has a note on each end, so it can't actually pass to the other end.
This is the simplest example I was talking about. That's all. But it is a combination of 2 waves passing each other that causes standing wave.
Yeah, and I can't think of any examples.
What's going on?
Do you think
So the last part was about standing waves. Standing waves. So the idea with the guitar was the first one we were talking about. When a guitar string is plucked, it vibrates up and down, causing a standing wave with nodes here. And there's only, and I think some of you made mistakes in the homework. I don't know if I misstated in the class, but there's only one antinode in this example.
Yeah, I made.
Okay, it's the midpoint where there are 2 nodes here and here. Okay, so a standing wave that we came up with in class, who was it again? Julian and is it you? You and Dylan that were standing on the chair over there. And the standing wave that they were able to produce was one
Let's do it again.
that looked like this. The Slinky's in the other room. And this example had a stationary point right in the middle of the Slinky, which was really cool. And what we'll notice here is that there are 3 nodes and only 2 antinodes. So what correlation is there always going to be?
1 plus X
And nodes, right? So again, here there are 3 nodes, those are the dots, but only 2 antinodes, and those are at the midpoints or at the maximum amplitudes. Those would be the antinodes there. Okay? 14.1. What was 14.1 again? Characteristics of light.
Speed of light,
Talked about the speed of light being finite. This was yesterday.
3 times.
Okay? 3 times 10 to the 8. We talked about the brightness or the luminosity of a lamp and how its actual brightness is really a factor of the distance from how far you are. So, and you can tell that obviously. You take a flashlight, look at it close up, it's going to hurt your eyes. When you back it away, it's suddenly not as bright. It decreases as a function of the distance squared. Okay, remember that? The distance squared. James?
And that's due to spreading?
Yeah. So it has to do with the fact that it's an area and it's spreading radially. And radially, it's the area of a circle is r
Does it
squared.
also change based on atmospheric conditions?
Sure, absolutely. Absolutely. Yeah, if it were in a vacuum, though, it would just have to be a function of the distance, yeah. We also, yeah,
If you were in a vacuum, you could shine a flashlight from one side of the United States to the other.
yeah, if there was nothing that was affecting it, a light wave should continue the entire way, yeah.
All the way back around.
And that's also why, like, another reference to the movie Gravity. Remember when he asked her to flash her lights? He says, flash your flashlight so I can see you. And she flashes the stop it. And she flashes the flashlight several times. And he sees that from really far away. Okay? Nothing is going to...
Snapchat space.
Stop. Nothing is going to affect it besides the actual distance traveled. Nothing that's in the air. So it does get less bright, but not as if it were on the earth. Like if I shine a flashlight right now, it wouldn't be really, apparent because of A, the apparent light around us, and B, because of the atmosphere itself. There was the third thing we talked about in that section, the EM waves and how radio waves are lower frequency and gamma rays are higher frequency. And the wavelengths are vice versa because those are inversely related. You should be able to identify applications of them. So if I said, for example, which of the following types of EM waves is used for thermal imagery?
Infrared.
Infrared. Okay, that was one of the ones we specifically talked about. Which one is used in, or which of the possibilities could be used for cancer treatment? There were two. Gamma and then also X-rays also. They were overlapping. Okay?
Wait, don't X-rays cause cancer?
Depending on the amplitude and the frequency. So X-rays could also be used to treat cancer. Okay, to kill cancerous cells.
So what's the difference with the wavelengths of, let's say, a flashlight that you shine on the side of the building, or something like the laser pointer that travels much further?
It's more focused. A laser is let me think of the acronym. Light amplification, spectrum, emission, radiation. Has to do with the focusing of the actual light, whereas a light bulb, it's using a convex lens inside of it, which is causing it to spread out. But a laser is focused light. It's very different. When you ever seen the inside of a flashlight, you see that lens in there?
Yeah.
Okay, the lens is made to spread the light so that it actually goes outward, which is causing it to decrease in its luminosity over distance. Whereas a laser, it's like a focus light. You're not worrying about the area as a result. It's pinpointing it.
So it doesn't square with distance? It doesn't follow that same rule, or?
I don't know for lasers, I'm wondering. I know for lamps and basic lights they are. I don't know if it changes. I mean, theoretically you would think it does because if you took like a laser pointer, although, I don't know, because we've always tested it on Earth. You never use a laser pointer in a vacuum situation where you're in space. But you would think that it would go on forever. I don't know, I'd have to research and look that up. I'm not sure about lasers. But if you were using a laser in a classroom, after a certain distance it would become a lot, less apparent. Sure, if you turn off the lights you can still see it better. But even then it would not be as bright or not be as focused on that spot. I don't know.
So what was the acronym that lasers did?
Light, amplification, I think it's like spectrum, emission, and radiation or something.
I never knew that was actually.
It's an acronym, yeah. Laser is an acronym for something. LASER, not ZER, obviously. Even though some people write laser with a Z for like laser tag and stuff. Okay, but it's an S. But yeah, it's an acronym. The last thing that we talked about in section 14.1 was using the formula V equals omega lambda, but what is the velocity for all EM waves? Yeah, it's that constant, the speed of light, 3 times 10 to the 8th. Okay? All right, let's stop here for the review.